Hello everyone, I have already explained about shear force diagram and bending moment diagram by using hand calculation and by the ANSYS Mechanical APDL Advanced Parametric Design Language. In this session I am going to explain you how to apply the concentrated load, uniform distributed load and moment load in a simply supported beam. If you had not seen my previous lecture, so visit the description box and click on link. First of all, you have to understand what is the meaning of advanced parametric design language. So now I am going to explain here what is the advanced parametric design language. First of all, so I have go to create a rectangle by using the value in ANSYS Mechanical APDL. Then after I have go to create the same rectangle with the application using advanced parametric design language. So this is your interface of ANSYS Mechanical APDL. So now I am going to create here one rectangular area. So the width is your 10th and height is our 6. So now come to the click on the preprocessor, modeling, create, then go to the area, then after go to click the rectangle and just I am using here the bidimensional method. So input the value of x1 and x2. So x1 is my 0 and x2 is our 10, and then y1 is my 0 and y2 is my 6. So simply click on OK button and just you have to watch here. So one models have generated here one rectangular area. So after creating of this area, so I go to delete this area, and then after the next I am using here advanced parametric design language. So how to delete this rectangle? So simple go to the modeling, then here option is given there delete, then now come to here the area and below, and simply I go to click here pick all. Next I have go to define here the advanced parametric design language. So first of all go to define here the parameters. So simple go to click on the parameter and a scalar parameter, and here is the section. So you have to input one parametric value. So suppose I am using here the width W is 10, and then click here the accept. Then the next I will using here the simple h equal to 6, and now click here the accept. So this is not a case sensitive, so simple, and then after come to here the close. So now again I have go to create one another rectangle in the same process. So now come to click on the modeling, create, area, by dimension. So I am using here the value is W, and the next I am using here the value h. So simple go to OK. So now again at present time create for one rectangle, input here the dialog box in W and H. This is your parametric value. So now go to close ANSYS, and then after open the new ANSYS APDL. So this is my new interface of the ANSYS APDL. So now this is your problem. So consider a simply supported beam loaded as shown in figure. Draw the shear force and bending moment diagram. So this is my R1 reaction force and the R2, and given here the concentrated load 10 kilonewtons, uniform distributed load 5 kilonewton per meter, and here given one moment load, so minus 10 kilonewton meter. So now I am going to solve this problem in ANSYS Mechanical APDL. So first of all go to click here the preferences, and then I am using the selection the individual discipline shown in graphics user interface is the structural, and simple click here OK, and then go to define the element. So already discussed in the previous lecture, so why I am using the beam 188, and go to the options and just you have to click element behavior. So change the linear form to cubic form, so already discussed in the previous lecture. So go to close. So now first of all I have go to define here the parametric value of the Indian standard medium flange beam. So I am using here the ISMB 200. So here given the all parameters value, so D, B, T and capital T. So now come to define as a parameter. So go to the parameter, a scalar parameter. So input the value EX will be equal to our 210 e to the power 9. Then click on the accept button. Then W1 equal to your 100 e to the power minus 3. Then W2 is your equal to W1. Then after your W3 equal to 200 e to the power minus 3. Click on the accept button. Then T1 equal to your 10 e to the power minus 3. Then T2 equal to your T1 click on the accept button, and then after T3 equal to your 5.7 e to the power minus 3. So accept and close. So after defining the scalar parameter, so now come to define the material property and go to the material model and a structural, linear, elastic, isotropic. So just input here the EX. And now Poisson ratio is my 0.3. Now come to define the sections, go to the beam, common section. So I am using here the name ISMB 200, then after go to subtitle, subtype is my I section, and now come to define here W1, W2, W1, W2, W3, T1, T2 and T3. So already the all parameter values are given in my parametric scalar system. So simply go to the mesh preview and then click here the OK. So all section parameter values are given there. So after defining I section beam, so go to generate here the finite element model, modeling, create key points in active coordinate system. So one number key point is my 0, then second number key point, so I input here the value is our 1, then third number key point is our value is the 2, and then after come to here the fourth number key point is our 4. The all values are given in your physical problem. Then 5 number key point is my 5, and then after my 6 number key point is 6. Go to click on fit view. So after creating the key points, so go to generate here the lines, click on the lines, a straight line. So first of all click on key point number 1 to 2, then after 2 to 3, then after 3 to 4, and then after 4 to 5, and then come to click 5 to 6. So here is one build up here the line, and then one another key point define in your active coordinate system number. Suppose I will say given here the 7, so key point number is our 3 and in Y is our 1. So why I am selecting here, so go to define in future so beam orientations through these key points. Go to plot and multi-plot here. So now after creating the line, so now come to the go as a meshing, and now so I am defining here the mesh tool, and first of all so we have go to define the element attribute as a global. So now come to set up here the lines and go to click sets and select the all lines one by one, and then simple click here OK, and then pick orientation key point. So at present I'm the no, so check the dialog box as a yes and then OK and select these key points. So already defined here why I am go to pick on these key points in the previous sessions. So then after go to define my size control as a lines. So this is my size control lines set, and the select here the all lines and define here my number of element division. So I am input here the number of element division is 1. So click on the OK, then after come to click on this tool and now go to the mesh and select here the all lines. So simply click on the because. So here is the generate here the elements. After generating the elements, go to define here the solution. So this is our next phase, and the analysis type new analysis as a static, then define loads, apply a structural displacement on key points. So at present I'm defining here the boundary conditions. So after selecting the key point number 1, so go to define ux, uy, uz, rotex and roty. So why I am not defining here the rotz? So at present time here is your pin connection. Simply go to click OK, then again come to the define the last key point, the key point number 6, and here is your roller supporter. So simply remove here the ux. Now you have to define the uy, uz, rotex, roty equal to 0. So after defining the boundary conditions, so now come to define here as a load. So now come to plot here the key points, and then after go to define the load. So my concentrated load on key point number 2 is given the value and fy direction is minus 10 e to the power 3 then click on the OK. Then after come to define as a pressure on beam, select the beam, then OK. The value is your 5 e to the power 3, and then after come to here the next as j5 e to the power 3. Simple click on OK. Then after apply here the moment, so go to the force, click on key point, select this key point and apply here the mz value, and this value is our again minus 10 e to the power 3 in the sense of minus 10,000 kilonewton meter. Simply click here the OK. So now come to here the plot and multiplot. So after defining this value, so you have go to simple solve current ls, and then solution is done. This is your very important step. So go to general post processor, read result first set. So come to click on plot results, then deform shape, deform and undeform. So this is your just showing here the deform shapes. So now also go to the plot control, styles and size and shape. Simply on here the display elements. So these elements look like about this manner. Okay, and also you have to animate this value. So now come to here the plot control, then animate, go to the deform results, and then after come to simply degree of freedom solutions, use sum. So here is just shown in your graphics as a deform shape. After showing the results as a deform shape, so now come to the watch what is our shear force diagram and what is our bending moment diagram. So now come to draw here the shear force diagram and bending moment diagram. So now come to define element table. So define table, and now come to click here add and go to select here by sequence number SMISC. So input here the value of 5, then apply, then now again go to click here by sequence number SMIC 18. So why I am defining here 5 and 18? So through this process you have to draw the shear force diagram, and already previous sessions we have defined why you have input 5 and 18. So now come to watch, click here the plot control and contour plot, go to the line element results, and now define here the 5 in I number node and 18 in the J number node, and simply OK. So go to zoom this model graphics, and now this is your shear force diagram of these problems. So the next is I go to compute and draw here the bending moment diagram. So how? So now come to again element table, define table, and go to the add by sequence number SMIC is values our 2, and then after apply, then again come to click here the by sequence number SMISC 15, simply OK. Then after come to click plot results, then contour plot line element result, and change here the value. Node number I is our 2 and node number J is our 15, and simply click here the OK. So this as a hand calculation, and now in this is your solve in ANSYS. So it may be shown here the sign convention, the bending moment diagram in opposite side. It may be the same. So thank you very much for watching my video.